Hello and welcome to the second part of the alloys tutorial. In this episode we'll talk about static modeling, and what I mean by this is modeling your domain by constraining signatures and relationships between those signatures, but will not define any operations on those signatures. You should also know that there is an accompanying blog post to this video, and you can find link to this article in the description of this video. Let's start by analyzing a very simplistic model of a bicycle. So here in a second line we are defining a signature called wheel, which unfolds into a set which contains three atoms: wheel 0, wheel 1 and wheel 2. And I described that using a pseudocode. It's a pseudocode because you cannot just copy paste that and compile it as an alloy code, but a very similar notation is used in examples description. We'll see it later. So here we define another signature, bicycle. There's nothing interesting going on here, but the interesting part are relations. So front and rear are relations, and front corresponds to front wheel and rear corresponds to rear wheel. And the question is, what is a relation then? So a relation is also a set, but it's not a set of atoms, but it's a set of tuples. So in this case, we may say that bicycle.front, one of examples of bicycle.front, is this set described here. So it's a set of three tuples, and this arrow corresponds, denotes the tuple, and in this case all the tuples are pairs, so all of them have two elements. In general, they may have more elements, but that's the case here. Let's try to run it now. So there is an instance found, and that's the first example. So we've got three bicycles and all of them share the same wheel. It definitely doesn't make sense, but given our specification, it's a perfectly valid instance. Of course, on our way on, we'll try to constrain our model more precisely so we can rule out this kind of ridiculous examples. But so far, so good. Let's take a look at different representations of this model. So here, using those buttons, you can switch between different representations of the same example. So now we are using visualization, but we can also switch to text. And here in general, you can ignore all those entries without a prefix this. You can treat them as a implementation detail of alloy tools. So we are mostly interested in those 4 lines. And in particular, you can see that here is the notation. The notation used here is very similar to what I used in comments right here. You can also switch to tabular representation, which is sometimes very handy, and you can also use the tree representation, but from my experience it is the least useful representation. So it's good to know that there are a few perspectives you can look at your example. And now let's move on to multiplicities. So when defining a relation, you can also define its multiplicity. And if you omit, then the multiplicity of 1 is assumed. So such formulation is complete equivalent to the previous formulation without those ones. But you can also choose from different multiplicities. So for example, we can define front as a lone, and lone means 0 or 1. And let's try it out. So now a bicycle 0 doesn't have a front wheel at all, which is expected because of the meaning of lone, which also includes 0. And we can also take a look at some other ones. Yeah, so it also includes 1, so it's basically a more broad, a bigger example than the previous one. The other multiplicity available is sum, which means at least 1. Let's take a look. It may take a while. By the way, you can see the number of relations here, so it may also help us to detect when we finally have an example with more front wheels, and that's the case here. So bicycle 2 has 2 front wheels, which is also according to our specification. Correct. And we also have set, which means any number of wheels in this case. So it can be 0, 1, 2, or any other number. I will not give you an exhaustive list of all possible multiplicities. You can take a look at, for example, Hillel Wayne's reference site to see more of them. But that's the general idea of multiplicities. It's also good to know that signatures may have multiplicities too. So, for example, I can state that there is only one bicycle, and let's try it out. So, as you can see, in all of these cases, I have only one bicycle, and probably will run out of examples quite soon. Yeah, as you can see. It's a pretty small solution space with only one bicycle. And it's also worth noting that this is different than specifying size of set as part of run command. So here we are saying that it's part of our model that there's only one bicycle. It's probably not the best example, and also you can use any other multiplicity. You can use lone, for example. But I think in practice, if you see a multiplicity of signature at all, it will be 1, and it is sometimes useful if you are working with some abstract values which don't have any physical representation. So, for example, you may have, let's say, a signature color or some specific color like red, and then it doesn't make sense to distinguish between atom red 0, red 1, red 2, and then you can have a signature of multiplicity 1. Okay, so we've learned that both signatures and relations are sets, but if you use other learning resources, you may come across various metaphors of what signature is. And for example, I've read that signatures are like Java classes, and it really made my learning process much more difficult than it could be. Mostly because I took this metaphor too literally. And let me give you an example what I mean here. So from time to time you may stumble upon something like this. And for me, back then when I stuck to this Java class metaphor, it was really hard to decipher what's going on here, because for me it looked like front being a type of a result of some type level computation, which takes as a parameter one type wheel and another type bicycle, and it was basically a completely wrong direction, and it doesn't help at all. But if you remind yourself that, well, wheel is just a set, 3-element set, and bicycle is another 3-element set, then it's pretty clear what's the outcome of this class. It's a set of 6 elements, and then everything is pretty easy. So, however, I know trivial it may sound here, it's the realization that everything in Alloy is a set is, I think, the most important thing to learn. And if you realize and understand it on a deeper level, let's say, then everything else is coming much clearer and consistent. Okay, so now it's time to finally work on our specification so it doesn't allow all those incorrect instances. I will remove all those leftovers. And so the first thing I want to work on is to enforce that within a given bicycle, front and rear wheel are different. So I can introduce a fact, and here I will state that for all bicycles the following holds, and it will say that b dot rear must be not equal to b dot front. And let's try to execute that. And as you can see, we don't have those weird situations when all bicycles were sharing the one wheel. They still share some wheels between them, but within one bicycle, let's say bicycle 2, the rear and the front wheels are different. So seems like the first fact worked. Here it's worthy to elaborate a bit on this part. So this is a quantifier, and in Alloy there are a few types of quantifiers. So you can say, for example, something like this, or repeat the same but for, say, a loan. And all those three are different flavors of the same construct. So the first one means that for all bicycles the following should hold. The second one means that for exactly one B from said bicycle the expression should hold, and the last one is similar, but it states that the same thing for at least one bicycle. So that's the general idea. It's also good to note that they are using the same keywords as relation multiplicities, but in different context, and they have different semantics here. So quantifiers are, I think, much more powerful and general idea than relation quantifiers, which have quite limited usage and meaning. When it comes to this particular quantifier, since it's a quantifier all and it uses a single variable, we can rephrase it using a syntactic sugar equivalent, which looks like this. So we can also omit this part, and we can access the relations without using dot notation or referring to any variable. So the following is exactly equivalent to what we had before. Let's try to run it, and it still looks very similar. It seems like the fact is still held all the time, so looks good. The next thing I want to work on is to restrict our model so it doesn't allow this kind of situations. So in this case, the wheel 1 is shared between 3 different bicycles, something we definitely don't want in our model. To restrict our model, we need to add another fact. So for any 2 bicycles, the following should always hold, and B1 front should not be in B2 front plus B2 rear, and we need to repeat the same, but for rear wheel. Okay, that should be enough. Let's try it out. Okay, single wheel. So as you can see, Ali was only able to come up with instances with no bicycle at all. So it suggests that we probably overspecified our model. So the reason for this is here. So all quantifier and all of quantifiers work that way that they do not assume anything about B1 and B2, and in particular it doesn't assume anything. It doesn't assume that B1 and B2 refer to different bicycle. So if it happens that B1 and B2 refer to the same bicycle, then this case becomes something like this, and it's becoming clear what's the problem here. So in this case, that expression is always false, because B1 front is by definition always in B1 front plus B1 rear. So to fix that, we need to assume or enforce that B1 and B2 are always different, or they refer to a different bicycle. So this arrow means the logical implication, in sense that we know from first order logic. So given that B1 and B2 are different, then the following should hold, and that hopefully should be enough to make it work. Let's take a look. So yeah, that's a good one, and the problem here is that since we restrict the number of wheels to 3, Alloy cannot generate instances with more than 1 bicycle. So let's limit the number of wheels to 6, and it should allow Alloy to generate some more interesting examples. Let's see. Okay, that's something non-trivial and also correct. So we have 2 bicycles and they do not share any wheel, and for both of them their front and rear wheel is different. So it looks like we made some real progress here. There is one thing that may bother you here, and it's code duplication. So we basically copy pasted that part from the line above, and you may ask, is there any way of extracting common code? And the answer is yes. So we can use functions for code reuse. So the syntax is as follows. So I will try to extract this part to a function. So we can call it all wheels. And for a given bicycle, we want to return a set of all its wheels. So it will be like this. And now we can use it here. All wheels of B2, and the same thing here. And that should be enough. Wheel. I haven't renamed that. Okay. And now the result should be roughly the same. Yeah, looks nice. And we can go even further, and we can try to define that as a predicate in this case. So since here we are returning a set of wheels, we used a function, but if the return type is Boolean, then we can use a predicate. So I will call it not in, and the first parameter will be a wheel, and the second one will be a bicycle. I don't need to define return type, and I will rewrite this whole condition. I can actually reuse the function also here. So all wheels of B, and now I can rewrite this whole thing in this fashion. So B1 front and B2, and also not in B1 dot rear and B2, and that should be the same. It should be square brackets. Yeah, let's take a look. Yeah, it yields the same results. So our small refactoring worked. So there is one more thing we can work on in this model. Let's take a look at instances generated. And the problem here is that that wheel doesn't belong to any bicycle. And while it's not necessarily incorrect, it is definitely not an interesting instance. So let's rule out those uninteresting examples, and we can do this by adding another signature fact. In this case, it will be in scope of wheel signature. So we want to say that any wheel has to be in a sum of bicycle front and rear sets. So and that should be enough to specify that. And as you can see, all the examples were one that are interesting for us, and yeah, the number of them is quite small, but that's because the model itself is inherently simple. So I think we are done with constraining our model. Now I'd like to elaborate a bit on this in operator. Let's consider in operator in general. So for any given A and B set, and let's say that A is a single element set, and B is a set of A, B, and C. And in this case, the whole expression A in B would return true because A can be found in a set B. But if we consider this case, then the whole expression will return false because atom A cannot be found in a set B. And what will happen if A contains a few elements? Then the whole expression will be true only if for each of elements of A, they can be found in a set B. And now you may say, but in this particular case, the keyword this in this context refers to an atom as opposed to set. So why I'm saying that A has to be a set? So that's the moment when some of Aloy's design decisions are becoming clear or apparent. So when I keep on saying that everything in Alloy is a set, I mean it in a sense that even atoms themselves are sets too. Those are single element sets, but still sets. This coherent treatment of everything as a set in Alloy brings a certain elegance and consistency into the language. And it's simply very handy for you not to need to worry about whether your expression is a set or an atom, because you know that it will be always considered a set. At the same moment, it may sound weird because you may think that it probably causes some ambiguity in the language. But that's not the case because Alloy doesn't allow nested sets. So you cannot have a set of sets. And therefore, it doesn't lead to any ambiguities. And thanks to that, you can enjoy this convenience of treating everything as set without losing any precision in your programs. So we are done with a bicycle example, and now it's time to move on to a small assignment. So the assignment is Einstein's riddle. It's a small logical puzzle, and the story is that there are 5 houses in 5 different colors, and in each house lives a person with a different nationality, and each of those owners drink a certain type of beverage, and so on and so forth. And we need to answer the question, who owns the fish? And we are also given 15 hints. They seem pretty random, but actually they are exactly enough to answer the question. So I prepared the basis of the model you can use to solve this puzzle, and you can find the source, the link to the source in the video description. And I already defined the model itself. It's of course only one of a few possible models, but it gives you a framework you can work with. And now your task is very well defined. So for each of those 15 hints, you need to write a predicate. And I already did it for 2 of those clues to help you get started. But your task is very clear, so you need to write 15 predicates, and the outcome is also easy to verify. So if you written your predicates correctly, you should have exactly one instance of your model, and you can also, having this one instance, you can check it out who owns the fish, and then if you click to the solution link, you will see whether your answer is correct. I will run the solution to familiarize you with the output and how to interpret it. And yeah, as you can see, the visualization is pretty big here, so I think it's much easier to use tabular form. And in this tabular form, I think it's not so hard to follow what's going on here. So, for example, Breed owns a house 1, and this house is of color red, and he owns cats, and so on and so forth. So in this case, it is a Norwegian who owns the fish, but the thing is that we have much more examples. So in this example, Breed own birds, and basically our solution is greatly unconstrained. So probably there are 1,000 of possible instances of this specification. So your task is to constrain it so there is only exactly one possible solution, and then you need to read this table in this way. You just need to figure out who owns the fish. So that's your task, and thank you for watching, and have fun